Okay, so welcome to today's colloquium, Heidelberg Joint Astronomy Colloquium. So today we have the pleasure to have as our speaker Paolo Molaro from Trieste, from the Osservatorio Astronomical Trieste. Paolo did his PhD in 1987 at CISA in Trieste, and then went to the observatory, where he also served in between 2000 to 2003 as the director of the observatory. And in the meantime, he had also been visiting for a couple of one-year visits to, for instance, in Paris and to ESO. And he works on metal-poor stars and primeval galaxies. And today, he will talk about astronomical probes of fundamental constants. So please, let's welcome Paolo Molaro.
Thank you very much. Can you hear me? Thank you very much for this kind invitation. I'm very pleased to be here in this very nice environment. And summer reminds me of Italy, but it's not like that. It's ready. Okay, the topic of today is about fundamental constants. And I know that this is not a very popular topic, so very English research. So I've been asked to try to be general, to make the topic enjoyable for non-experts as well. So the outline of my talk will be first to define what is a constant, a fundamental constant in physics. Second is why we think it may vary. Third, what are exactly the constants that astronomy can deal with, can measure, and can probe, and then passing to if actually they vary or not, and describing what we know about the field at the moment, and to end with some perspectives of the future. So what is a constant? I cannot really read from here. I will introduce this with a reply of Einstein to Rosenthal Schneider in 1945. Einstein wrote, with a question of universal constant, you have branched one of the most interesting questions that may be asked at all. There are two types of constants, apparent and real one. The apparent are simply the outcome of introduction of arbitrary units, but are eliminable. The real ones are the genuine numbers which God had to choose arbitrarily, as it were, when he designed to create his world. And what I'm really interested in is whether God could have made the world in a different way. That's to say that the constants, the fundamental constants, are the end of any theory that we have of the nature. When are the things that we cannot really predict, but we can just measure. So if we go to the standard model of elementary particle, we have a list of about 28 fundamental constants. Four are the fundamental coupling of the four interactions: gravity, weak interaction, strong interaction, and electromagnetism. And then there is all the mass sector with a mass of leptons, bosons, and quarks, and how they mix together. The exact number of fundamental constants depends on the theory. If you go to the supersymmetry theory, there are a lot, much more. If you go with grand unification, you unify the coupling of fundamental interactions, so you decrease the number. So the number, the exact precise number, depends on the theory which is behind. Nevertheless, these are actually measured constants. And the standard models say that they should not change. They don't change after 10 to minus 6 seconds. However, is the reproducibility of the measurements that tell you if they change or not, and why. So the assumption that they are constant actually is an assumption that is not, they cannot be verified. It's interesting to point also what Hoyle wrote back in 1964 in a paper on the New Science, when he was writing on what will be in the astronomy of 1984. And sorry, I don't know if you can read it. He wrote in the piece of the paper, my suspicion is that important long-range coupling do exist, and that many of the quantities we normally think as constants are subject to a slow variation with time. By slow variation, I mean slow compared with the rate at which existing galaxies are moving apart. On this basis, the precise values of some of the key constants of physics will have no absolute significance. They would simply belong to that at which they happen to live. So it was a sort of a generic consideration. But why we think that fundamental constants may change, may vary? I mean, that is almost an unavoidable outcome of all M theories or superdimensional theories, where the constants are effective and are defined of the multi-space. And if you have the space are varying, then fundamental constants are varying as well. So multidimensional theories predict always variable constants. Another effective way in which the constants they can vary, if there is a coupling of a presence with a scalar field with a matter radiation. And if we know today that scalar fields are actually part of the nature, the Higgs field as we discovered, and there are many scalar fields which enter in many fundamental theories of astronomy. And I remind you, inflation is related to scalar fields, with strings and superstrings as well, and moduli fields. Any theory of modifying gravity is, the modification of gravity is theoretically predicted, including some scalar fields. And important for astronomy, the quintessence, which see a slowly evolving scalar field, which can produce negative pressure and explain the acceleration of the universe, can be produce some variability of the fundamental constants. And so that should be of great importance for astronomy. And if you can connect a variability of a fine structure, for instance, to the cosmon producing the acceleration. So, however, we don't have a theory of a variability of fundamental constants. We can just search for them, and if we find some variability, this means that there is something new that has been detected. If we don't find, and possibly related to the scalar fields, but that has to be verified. On the other hand, if we don't find variability, this means just that the equivalent principle of general relativity is true at I z. And this is extremely important to be verified, because extend the domain of validity of our physical laws. So all these theories actually don't tell when, at which level the fundamental constants may vary, so you just have to go to observations and measure them. There is no, unfortunately, there is no a clear number of them. So what are the constants that actually can be measured today in astronomy? The first one is the alpha, fine structure, which has this value, not this one, and which is connected to electromagnetism. And another important dimensionless ratio, poor number, is the ratio between the electron and the proton. What does it mean actually this electron to this ratio to be important? Because the electron is an elementary particle, we know it has this value, and is connected to the weak scale because it's a vacuum expectation value of the Higgs field. The proton, on the other hand, is not an elementary particle, it's a complex particle. And if you go and see the construction of the mass of a proton, actually there is a small, which is due to the quarks, there is a small component from electrodynamics, but the most come from the gluons. So the proton actually is made, the most part of the mass of the proton comes from the gluon, so the strong force. So when you measure the ratio between electron to proton, actually is at first order, is you probe the ratio between weak and the strong forces. Of course, many astronomers try to measure also the variability of the gravitational constant, but this is a dimensional quantity. And so if you find actually varying, it's good for making bounds, but if you find them vary, then actually you don't know exactly what is varying behind. So actually, I don't want that it's useless, but I would just to say that it's less clean. In particularly if you find the variability, because in this case all these probes assume that the other constants are not varying. So actually I confine my talk only on alpha and mu. Well, these are actually constants that have been probed by our colleagues physicists in the lab. And alpha is probed by comparing atomic clocks. And by comparing mercury and aluminum, for instance, the best result is of the order of 10 to minus 17. So you don't have variability of the final structure at this very small value, 10 to minus 17 per year, which is amazing. It's just like having a few seconds of error along the age of the universe. You can establish that the age of the universe is 14 giga-years plus or minus few seconds. And it's amazing. Just using this one, you can also constrain mu at the order of 10 to minus 15 with using other atomic clocks. So what about the astronomical measurements? The most clean come from absorption line quasars. You see that this is a spectrum, high resolution spectrum of quasar, and imprinted in the spectrum there are a lot of elements, lines, which are due to the elements of a foreground galaxy, and the quasar is just of the background, illuminated by the light of the quasar here. And these are all the lines of an alpha forest. But these are atoms, and you have imprinted here in the spectrum is just the atomic structure, the structure of an atom in time. So if you go and if you measure the atoms, you can have information of the fine structure and the ratio of electron to proton mass ratio. These are all the scaling. For instance, of course, you have also the gross structure of an atom depends on a Heidelberg constant here, but that's not useful because it will change the redshift, and so you cannot discriminate between a change of alpha or a change of redshift. The important things are here: the fine structure, which depends on the alpha square, or hyperthin structure, which depends on alpha square and the proton geomagnetic moment, and also mu. Okay? And if you go to the molecules, the molecules have different scaling with mu, depending if you are vibrational levels or rotational levels. One is the square mu and the other mu, and you can use this difference, as we will see, to make counts on this variation. But apart with this, it's important that all transition actually depends from alpha. And so you can actually, and this has been implemented very recently, I mean in 1999, if you go, and this is at the core of the method that we use today. I mean, all the lines have a different sensitivity from a change in alpha. You can see from this equation here that is a dependence from Z, that the light elements don't have sensitivity from alpha, while heavy elements do change a lot. And the change here, which is highly exaggerated, these are the common absorption lines which are detected in quasar spectra. So you can in principle, you need to make a bound to a change of alpha, you just need two elements. One which does not depend on a change of alpha, compared to one which depends on a change of alpha. And these are the lines, and the sensitivity to alpha is encoded in the sensitivity coefficients, which is here. You can have both positive or negative shifters. And if you have systems at low redshift, you compare generally iron with magnesium, while at high redshift you compare always iron and with aluminum silicon. Interestingly, is iron which has both positive and negative shifters. This is a model, a simulation of a change of the order of 10 to minus 4, which corresponds a shift of 2 kilometers per second in the line spectrum. You can see here that there are two magnesium lines which do not change at all, while the iron lines, which are positive shifters, are shifted by about this quantity. And this, of course, is easy to recognize, but the point is that not to go down here, not to 10 to minus 4, but to much lower values. So you go to reach about 200 meters per second or 20 meters per second to go to level to 10 to minus 5 or 10 to minus 6. So that's the method, and this was the first result that provide evidence that alpha was lower in the past. And we came out in 2004 with analysis of 134 absorption systems. And you see that you have a 6 sigma evidence altogether that alpha was lower in the past. This work has not been supported by other observations, including my own here, and a small group made not at the CAC but at the DNT. And you see here we analyze single cases like this one, for instance, and achieving a very good sensitivity of the order of 2 parts per million. Okay, we are maybe here probably at the level of 10 to minus 6, and also here, and there is no evidence for any variation. The same group provide variation using the KEK data, analyze the full VLT data. So here there was a disagreement between the two telescopes, right? And actually, quite recently, the Webb et al. Analyzed all 153 absorbers along 60 quasars, and this is all the result. And they did not find any variability of alpha, like we did before, along individual line of sight of small groups. But what they did is the following. You can see that if you combine all the systems from the two telescopes, you don't see any variability in alpha. But they noted that, and actually it was completely flat here, you see, but they noted that particularly high redshift, the KEK was giving lower values, while the DLT was giving higher values. So they tried to have a different fitting of all the data, not in time, but in space. And they fit a sort of position variability in the sky. And they found that all the data we are using a dipole model, the most simple dipole that you can think here. They found evidence for dipole. These are all the KEK data, and these are the VLT. And they found this is the direction of the pole, and with an amplitude almost of 9 parts per million here. And with a monopole contribution as well at this significance. They did also many tests. For instance, the dipole, the two sample KEK and the T can be treated separately. And this is the direction of the KEK data only. And this, the blue one, is the direction of VLT data only. You see that they overlap here quite well. They also, the direction of the two poles overlap for low and high. If you use a Catholic ratio to low and high, because they low and high include in both different lines. And also there is a consistency between the two data sets in the equatorial region of the dipole. So that seems to be convincing. Sure.
Sorry, were the data sets analyzed by in the same way by the same group, or did they rely on, say, observatory production pipelines, one for the DLT and a different one for Keck?
It's the same group that analyzed the Keck.
But using the same techniques for both data sets?
Yeah, probably yes, I would say.
Can I follow up there? Have they observed the same object with both facilities? I mean, after all, much of the sky is accessible from both.
No, they don't. But if you wait, I will show you one case in which we have tried. Okay, but there are a few things. I mean, in the equatorial region here, you can see that the blue points agree more or less with the red ones. So, I mean, there is a consistency in the equatorial region between the alpha values between the two telescopes. One concern that they put very recently is about the magnesium. Magnesium has an isotopic composition which is assumed to be solar. But actually there is no way to know what is the magnesium isotopic composition of these systems, because you cannot resolve the contribution of the two lines. And if you are varying the relative abundance of magnesium 25 and 26, you can change here the line position of the line, and so you can change the alpha, the velocity share. They introduce change this isotopic composition as a free parameter in all the sample, and they found evidence that actually there is an increase of 25 to 26 isotopes of magnesium going back in time. And if you do that, this change the dipole in the sense that this is the old dipole, this is the new dipole, the monopole is going to disappear and the effect is more enhanced. I want to say that if it's true, and we don't have a theory for that. I mean, the only idea that I found in the literature is has been elaborated by Keith Olive, collaborators, which imply that we live in spatial discontinuity, and here we have in the universe, in the universe, and this discontinuity comes from probably the inflation period, where you have a scalar field coupling with cosmic, the scalar field of inflation, producing a different values of alpha on large scales. In the last years, we started a large program at ESO, which was oriented to specifically to alpha, to probe the variability of alpha. I don't want to tell you all the details of this program. The target selection, which are the brightest quasars, where the more systems, etc., and was selected before the discovery of a dipole. Anyway, one star here, one quasar here, was pretty close to the pole and also relatively bright. Here is the color is the brightness. And so we started to analyze this quasar. This is a composite spectrum, and there are 4 absorption systems used for here. I'll skip all the details. And this is one of the most interesting systems. These are the lines that are observed, and we analyzed all the absorption component with a VP-fit code version. And we use, in our analysis, it's called the blind analysis. So we do the analysis in few steps without knowing the output for delta alpha over alpha. In particular, we first model the old absorption, and only when we have achieved a good statistically satisfactory modeling of absorption, we introduce the possibility of a variability of alpha, because it induces a very small shift in the line position. And when we did this, these are the lines already involved in the determination. This is the result. So we don't detect any variability of alpha, while the expectation of the dipole is over there. Depends on which model you take for the dipole. If you take dipole plus monopole, the prediction is free, so it's consistent with errors. But if you take the dipole only, the prediction is almost a delta alpha over alpha 7, or a value 7, which is up here, while we don't see. Of course, if you consider all the errors, that does not invalidate the dipole prediction, but certainly does not support strongly because we found a lower value of what expected, in particular on the dipole-only model. One thing that we did here is to introduce some possible or systematic origin in the analysis, which we know comes from the data from the spectrographs. We knew that because if you look at the position of the lines, we should not change for alpha. Actually, we found some variability in that it was revealing that some lines move in a strange way in the spectrograph. And this was also the result of another paper which used to compare the calibration of the spectrum by means of the thorium-argon or the iodine salt. And they also revealed, you see, strange structure in the order. But intra-order distortion exists in the spectra. We recently found also for the ARPS spectra, which is supposed to be the best spectrograph in the world. And this is actually due to the CCD. Here you can see where in the ARPS they make a pilot experiment of the laser comb frequency calibration. And by using the laser comb calibration of the solar spectrum and comparing the same spectrum calibrated with thorium-argon, we reveal that there are big distortions in the ARPS spectrum of the order of 100 meters per second going along the border. And this is amazing in a spectrograph which, deliver accuracy of radial velocities of the order of meter per second. And so you have these inter-order distortions which are due to the CCD, because you can see clearly the structure of the CCD, which have in the manufacturing there are sub-unities of the CCD of the order of 512 pixels, which can see here in the flats, in the technical flats. And this reveals that the pixels are not equal along the junctions. And when you calibrate the spectrum with the thorium-argon, the thorium-argon does not contain enough lines to recover all these differences and make this distortion, which in ARPS are present and are fixed. And but who knows, in UVS or NIRS, probably they are present, so probably are not fixed. So anyway, we made another experiment. It was, just to answer the question before, we took a quasar and with several absorption systems, and we observed this quasar from 3 telescopes. And Keck, Virti, and Subaru for the first time used for the for this work. And we tried to compare not only alpha, but to compare the spectra directly in order to break the systematic degeneracies between the spectra. And we found strange things. First, of course, when we compare the spectra with by means of the iodine cell, we found the same inter-order distortion in the Subaru as in the other telescopes. You see the single points here are positions within the single orders, while the black dots are averaging over the order.
Can you just briefly say what you mean by the same? just qualitatively the same number?
Qualitative, yeah, the amplitude is comparable. The amplitude is of the order of 200 meters per second. Of course, we cannot really trace the shape. So you have in the intra-order differences of the order of 200 meters per second on the single position. And another thing that has been revealed here, that when we use also the asteroids provide the solar spectrum, and we use the solar spectrum as an absolute reference. So these differences here are between the quasar and the solar spectrum as provided by Kourous. And you can see that there is also a long wave drift. So the spectra are actually stretched along with wavelengths, and there is a slope here which is very difficult to compute. It's the order of 60 meters per second over 1,000 angstrom here in the case of Iris. But more intriguing, there are also different stretching of the three telescopes. These are this is the Subaru spectrum with all the beta lines here. This is the Iris spectrum with all beta lines, and where we compare. And we compare the wall spectra, and you can see that there is a slope between the two. And this means that the wavelength scale is stretched. And we found also similar things between the VLT and the Subaru. So all the three telescopes are not on the same wavelength scale. We correct for that. Okay, these are just an example of the systems. I'm going with time. This is one of the systems, and up to a redshift, this redshift, and this is a second system of the three. And this is the result, just a numerical result. You can see here the different colors, the three telescopes for the three systems. And you can see here that more or less they agree. After all the three telescopes now agree, and they have they agree also within for every single system. So we are entitled to average everyone for a line of sight, and we found this value with this precision. We try to incorporate in this analysis all these systematics. Of course, the intra-order dispersion you cannot correct because they are not fixed, not predictable. So we just we put the random distortion in the spectra with the same amplitude, and we measure the delta alpha over alpha as the outcome, and that says evaluation of our systematics, and also the other systematics for the slope, which will be corrected using the asteroid observations, and also for the correlation between the pixels and so on. So these are, for the first time, determination which include the systematics. This is consistent with zero, but although it's quite negative here. And if you compare with dipole, is this one, this value here, while you should expect zero value. So that's also means that we cannot have full control of the systematics after all. And so the question is the dipole due to this kind of systematics? Well, the answer is difficult. It's quite possible, but of course you must introduce or think about a certain level of conspiracy to having the different systematics in the two telescopes producing the dipole as it's been observed. Okay, that's all for alpha. Let's go now to the second fundamental constant that can be probed is this ratio. As I mentioned, can be probed using the different sensitivity of rotation and vibrational levels of molecules, in particular molecular hydrogen here. This has been predicted by Thomson in 1975, and it's interesting that Thomson told me that this was actually a suggestion from Fred Hoyle. And when he submitted to Astrophysical Journal, he had problems to get accepted. And the referee of the Astrophysical Journal was Jeff Barbridge. So yeah, the paper suggested by Oil, rejected by Barbage, and then Oil convinced Barbage to make it published, and Barbage accepted, saying that actually will never be proved. The method was so theoretical that could never be proved. That actually you had to wait till the first time that has been implemented was in 1993, after 20 years that this paper was published. And you can see here all the Lyman and Werner lines here compared to the sensitivity coefficient here, again, which gives you the sensitivity of these lines to a variation of mu in this case. And again, you have all these lines and you have this sensitivity that move in one way or the other when you change the ratio of value of mu. So actually this is theoretically computed, and this you measure these velocities here and you probe again. It's a very similar way to as is done for alpha. So the problem here that we have very few systems. Molecular hydrogen is the most abundant molecule in the universe, but is very rarely observed. This is a collection of actually the fraction of H2 over total H, and you see that actually you need, since the rest wavelength of Lyman and Werner bands are around 1000, and so you need actually a redshift greater than 2.5 in order to place them in the optical band. And these are the first quasars which have been used since the beginning. This, unfortunately, is very interesting at 4.3, but is very faint because it's 19 magnitude, so this is not being measured. And the first one was this one in 93, which is, however, is a proximity of system that's close to the quasar, so is not really very suitable. So the first two were these ones that have been probed since the beginning. One other very difficulty is that the lines of molecular hydrogen sit in the Lyman alpha forest. So you have these lines here against a very regular continuum, and then you need very high resolution as well in order to pick them up. The first work were on these two quasars, as I said, to these two systems, and actually it came out as a detection of variability at the beginning, and you can see here by Reynolds and Paul. So, then the same data was revised by Thomson, which concluded that there is a marginal possibility of a shift in this quasar, and we measured the lines here. These are about 60 lines in this quasar. You can see that this is the radial velocity against coefficient sensitivity. Any variability of mu comes as a slope here. Okay? If your eyes can see a slope here, that is a change on mu at the level of 10 to minus 5 in this case. Okay? And we don't find here, and this is also found by King et al. in 1911. The new quasar that we observed very recently is this one. It is a new one. They are very handful. And in this case, we could detect more than 100 H2 transition up to J, up to 6. And we make all the analysis, but also in this case, we don't find any variability of mu at the level of 8. Another interesting method which has been suggested quite recently involves the ammonia molecule. This is the ammonia, the inversion transition of ammonia, where you have the nitrogen going up and down, and there is a tunneling, a tunnel effect, which produces the inversion transition of 23.7 gigahertz here. And Flambaum and Kozlov show that this transition, the inversion transition, is very sensitive to a change of the variability of mu. Is almost 2 orders of magnitude more sensitive ammonia compared to molecular hydrogen. the K. The K value is -4 here, while in the molecular hydrogen was 0.04. And the problem is that it's not standalone, so you have to compare the ammonia lines with other lines, molecular lines, and the most important problem is that ammonia is very rare in the universe, and there are so far only 2 detections, one at 0.7 towards this quasar here, and another towards the second quasar here at this structure. And you can see that here is plotted the ammonia line here, together with the other molecules which are used for reference. And also in these cases, there is no variation of mu at the level of less than 1 part per million. Okay? And a further more interesting molecule is methanol, and which has this structure, and the sensitivity is huge, is even 1 order of magnitude more sensitive than ammonia, and 3 order of magnitude more sensitive than molecular hydrogen, and is also standalone. It's the same galaxy that was detected for ammonia is also methanol here. And by using this, our observations from Heidelberg here, and you see that these are the sensitivities from the 4, comparing the phys-4 transition, which here there is no systematic because they arise from the same molecule. They give what is the most sensitive limit to use so far, which is at the order of 10 to minus 7 about. So here, so the summary, there is no evidence at all of the variability of mu so far, both comparing with the molecular hydrogen here or the radio measurements. And the weighted mean of the molecular hydrogen at high redshifts is over this one. So let's conclude. Just one more thing is the ammonia is very rare. How much time I have?
A few minutes.
Okay. Just this to mention, because ammonia is very rare in the extragalactic universe, but actually is very abundant in the Milky Way. And we use this method of ammonia determination in molecular dense core in the galaxy, where you have a lot of ammonia to other molecules. And these dense cores are very small, very cool. They are very, there is nothing happening actually there. There is no star formation in some of them. In most of cores, you have star formation, but there are some dense cores that are very quiet. And so and these are excellent gravitational laboratories. And with Heidelberg, actually we measure ammonia in several of these dark cores, and with a precision in the positional velocity of ammonia of the order of 1 meter per second. And we compare the same way with other molecules here, and we thought for a while to have found a signal there, because our estimated statistical and systematic error was much more than the signal. And however, we tried to repeat that, and was more than two years of work about that. And we couldn't reproduce that result with Heidelberg, and we also observed with other telescopes, and we could not find any variability, any change in the radial velocity between the lines. So we thought that the previous result was due to a systematic effect, and actually now we provide an upper limit to the mu in the galaxy at the level of 2 × 10⁻⁸, which anyway is the most precise astronomical measurement in delta mu over mu. And that's all. I want just to conclude to mention what we are developing a new instrument. Of course, the existing spectrographs, UVs, IRS, and Atsubaru are not ideal for this kind of work because of all the systematics that I tried to describe. And so we already we try now to make a new spectrograph, which is called Espresso, which stands for shell spectrograph for rocky exoplanets and stable spectroscopic observations, which was conceived also for this kind of work. This is the team, it's a collaboration between Geneva, Porto, and Lisbona, and Spain, and Italy, and is of course with all these people. So what is Espresso is a high resolution spectrograph to be put at the incoherent focus of the VLT. So it will collect the light from all four telescopes. It can work with one light with one telescope over all four together. And there will be an optical coudet range that brings the lights from the single telescope over there. And it is essentially a super ARPS spectrograph, so it's in vacuum, thermally stabilized, and hopefully it will not have all the problems shown by the existing telescopes. We started in 2007, and now we are making it. This is the CCD, the first CCD, all right, we are just trying to assemble, and I think in a couple of years, probably at the end of 2016, we will make the first observations, and hopefully will clarify all these, the issue of the variability of the claims of variability of fundamental constants, and we can foresee an increase, at least with the meeting of the systematics of the order of factor 3 or 4, and possibly one order of magnitude in sensitivity in alpha and in mu of the present determinations. And of course, more we will come if we succeed to make also a similar high resolution spectrograph to the extremely large telescope video. And that is my summary. I felt that the study of this variability of fundamental constants is quite important to establish the validity of physical laws in the universe. And if we can actually detect the variability, that will be a huge importance because it can be connected with several interesting things, including quintessence or error, which has to be, of course, tested. And at the moment, the most promising constants are alpha and mu, and I have to say that there is no clear the evidence of variability of any of these two constants at the moment. Therefore, there is a spatial dipole, which is on the table, which is a 4 or 5 sigma detection, so it needs to be studied. And I think that the future is bright because in the few time, 2 years, we will have at least Espresso at the VLT, and that's all.
Thank you for this very interesting talk about fundamental constants. Are there questions? Matthias?
Wouldn't the 21 centimeter line of neutral hydrogen be an ideal target for measurements of the variation of alpha?
Yes, it is, and has been used as well. The point is the 21 centimeter line is also, it comes from a hyperfine structure, so is you have dependence not only of alpha but of the mu as well. And so you have two constants varying, so you have to decide which one it is. But of course, there has been a lot of work on that, comparing the 21 centimeter with UV lines, and they produce some results with no variability so far, I have to say, for the both constants. But yes, I couldn't go in all the...
Just wondering about it.
Yeah.
So you showed that currently the alpha limits are dominated by systematic errors. In your last transparency said espresso will do 1 to 2 orders of magnitude better. Are the current systematics well enough understood that you know what to do to overcome them by a factor of 10 or 100?
Well, I don't think that that could be an exaggeration. I mean, I don't think that the present data probably are dominated by systematics. I would say that photonic noise and systematics more or less equal. So if you have espresso and hopefully is systematic free, you still have the photonic noise, which is not negligible because the systems are faint and you cannot beat them too much. Even if you are systematic free, it will be difficult for a 17 magnitude quasar to measure a single line with a precision of 20 meters per second, which is what you need to get to an order of magnitude.
Further questions?
Initially, you said that many of the, say, extended theories beyond the standard models are basically predicting that the fundamental constant should vary. Now, as far as we can tell, there's hardly any variation. Are all these theoreticians coming up with these ideas now very frustrated, or what should one take from it?
Well, they can predict easier lower variability.
Okay, so this is still compatible with conceptualism.
Yeah, sure. You just the only thing that you need to do is just to lower the coupling. Since the coupling is not constrained by anything, you just assume weaker and weaker coupling, and you may have a level of variability of the fundamental constants which is below your level of observations. But actually, if you increase your level, you just put you put a constraint on the level of this coupling.
Actually, that makes me wonder, because if there's really, in that sense, really no constraint whatsoever, no real prediction for that, on the log scale, that variation can be anywhere. It could be at 10 to the minus 100 or something. So, to be provocative, what makes there a good argument then to say, well, let's go 1 order of magnitude deeper into the accuracy if we don't even have any idea where this variability could pop up?
Well, one good argument is that actually you have a dipole variability on the table, which you need to answer that is true or is not true. Okay, that just sets a level which probably we will be able to do it with a better spectrograph. And the rest is, I think, is shot in the dark. I mean, you don't know, it's just that. But I think that it's extremely important to understand that the physical laws are the same. Because we know that there is something in the universe, right? That we don't know what it is. I mean, the dark energy. So the logical, the most logical thing is that there's a field, a scalar there. And so the hope is that you can prove that. And if you can connect the two things, you can, using the variability of alpha, you can reconstruct potential which is behind the scalar field.
To be clear, the dipole results, did that analysis take into account these CCD discontinuities and stretching effects?
No, because that actually came from our work, which is after. Sure. As just I commented before, I mean, that could be an explanation. But at the same time, you need, as I say, the conspiracy, because the same systematics have to work into different directions in the two hemispheres anyway.
Any further questions? Okay, so then I would say let's thank Paolo again.